not going to use nuclear overhauser effect NOE. And what is this phenomena? So this phenomena you can observe with the proton decoupled C30 NM. Proton decoupled C30 NM means broadband spectrum. So completely decoupled. How many carbons are there? Okay, that many signals you are going to get in the C30. And that intensity of the signal for a given C13 is going to increases versus the proton coupled spectrum. Okay. For example, if you are having CH3 and if you are having CH2, if you are having CH, the intensity of that CH3 is going to be higher, CH2 is going to be lower than CH3, CH is going to be lower than CH2. The intensity of it is going to change with the number of carbons which is attached with the particular carbon, number of hydrogens which is attached with the particular carbon. So this proton decoupled spectrum is proportional to the number of protons which is attached there. Number of protons which is attached there. If it is attached with the two, so two protons are attached to that carbon, you'll have two. So intensity is different. If the three protons are attached with the carbon, you will see the different attachment. So signal intensity is different. So why it is increasing and then decreasing? This can be explained. The increment and decrement of the signal intensity can be explained with using the effect. We call it as nuclear overhauser enhancement. Nuclear overhauser enhancement. So this effect is general. You can see in proton NMR, C13 NMR, or any other NMR also. You can see this effect. It is in general, and then it is going to appear anytime when one of two types of atoms are irradiated. So one of two types of atoms. If you are irradiating two similar atoms like two carbons, no, you will not see any nuclear overhauser. If you are irradiating carbon and then hydrogen, and these are two different nuclei, right? So you can see nuclear overhauser NOE here. NOE here. This particular hydrogen nucleus is going to have an effect on the carbon, and carbon nucleus is also going to have an effect on hydrogen. That means this effect is general and it appears when one of two different types of atoms is irradiated. So this spectrum of the other is observed. In this case, we are in the C13 NMR. We'll see the hydrogen population is irradiated to saturation and the C13 is observed. Hence, a heteronuclear effect is there. Heteronuclear effect means so carbon and hydrogen is not similar nucleus. Hydrogen is a different nuclei and carbon is different. At this place, when you are irradiating the hydrogen population to a saturated state, when you are irradiating the hydrogen population to a saturated state, the C13 is observed saturated state and you are going to observe the peak of the C13. And these saturated protons, the saturated proton nucleus are going to have an effect on the C13 nucleus. So this one we call it as heteronuclear effect and the effect can be positive or negative. Okay? The effect, whatever the effect is showing, that can be a positive effect or that means it can increase the intensity of the signal or it can decrease the intensity of it. There are two different types. Okay, but saturated protons means okay. Are you there in the decoupled techniques class? Are you there in the decoupled techniques class? So now I am asking you, are you there? You forgot. Very good answer. I like it. Okay. People, okay. What will happen when you are having the carbons and then hydrogen? Yeah, no. I will explain. Don't worry. Just I ask you whether you are there at that class or not. Okay, when you are having carbon and then hydrogen, we will give one frequency and then we will irradiate the. So this frequency we will give in such a way that it is going to irradiate all the hydrogens. That means all the hydrogens will be irradiated at a same level of frequency. That means they will go to a saturation state. At that saturation state, they will not have any effect on the signal. They will not have any effect on the signal. At that time, and you are going to give a second radio frequency to irradiate the only carbon. And these carbons will be excited, and then you will see a alpha state and then beta state, and they will have a differentiation, and then you will get a signal from here. So when your protons are in the saturated state and you are going to give the second radio frequency to the carbon. So these are not going to have any effect on this carbon nucleus because they are in the saturated mode. There is no energy differentiation in the lower and then higher for any other proton. All are equal. All are equal. This type of situation we call it as saturation state. Okay. So here, if you see, the effect of the nuclear overhauser can be a positive or negative, but most of the cases, like especially the C13 and then hydrogen, this effect is going to be a positive. So there is a possibility of positive negative, but in this case, C13 hydrogen heteronuclear case, this is going to be a positive. And how much it is going to increase the intensity of the other thing? That means so. Once C13 is there, another nucleus will be there. And this population of this nucleus, proton nucleus, will have the effect on this. So what will, if it is a parallel effect, the C13 and then hydrogen population effect is parallel effect, and slightly this particular frequency, the intensity of this, so it will add to this and then it is going to increase slightly with using it. So this can be the enhancement can be observed with using the NOE. This is the NOE maximum. You can calculate it with using the first irradiated and second is observed. So irradiated by observed, you can observe the things. So how much it is going to increase that. The total predicted intensity, you can see 1 plus NOE max. So whatever the gamma value is there, so what is the gamma value is there for the irradiated protons and then gamma value is there for the observed protons. So you can substitute here and then get the NOE maximum, and that can be the total intensity you can calculate as 1 plus NOE maximum. So this one represents the intensity of the bare carbon or something, and this NOE max is going to be additional to the bare carbon. For hydrogen and then carbon, the NOE will be 1 by 2, 267.5 divided by 67.8. This is the irradiated gamma value and then this is the observed gamma value. Irradiated and observed. So you will have the NOE value is 1.9. If you take this bare carbon signal as a 1, so the NOE value will be 1 plus 1.988. So 1 plus 1.988. Okay. So this much 2.988. So totally the signal intensity will be coming as 2.988. Like this, the intensity of the signal is going to increase with the influence of the proton nucleus which is there at the saturated state in the decoupled spectra. So this one we are going to have this one we are going to call it as nuclear overhauser effect. Okay. So 1.9 is this is very close to 2. Okay. So the enhancement will be there almost 200%. If you take it this 2, if you take it in the percentages, so you are going to get the 200%. So you are going to get the enhancement, maximum enhancement of this nuclear overhauser effect is 200%. Okay. So this NOE operates in both the directions. Yeah, that's what. Opposite and then parallel. C13 nucleus is there. If it is decoupled, it is going to enhance the signal of the hydrogen. However, the signal would be weak due to the low abundance of the C13. Low abundance of the C13. So, if you observe the carbon and hydrogen, hydrogens can also enhance the carbon intensity, peak intensity. Carbons also can enhance the peak intensity of the proton. This effect you can see in the proton atom, but the intensity will be very less, very less. That's why we did not read this topic in the proton NMR. I have shifted it to C13. Hydrogen will have more effect on this carbon signal, but carbons cannot have that much effect on the hydrogen because of its low abundance. The availability is very less. Right? C12 abundance is very high. C13 abundance is very less. Because of the availability of the C13, less abundance of the C13, you will not see the very good intensity, very high intensity you cannot see in the nuclear overhauser effect due to the carbons. This NOE for C13 and then carbon is going to operate in the opposite direction. Okay, and it is useful probe into the structural assignments also. How much the effect is there? So how much enhancement is there in the particular signal? That particular signal enhancement also will give some information in that while having the so whenever you are going to have a structural information, when you are calculating the structural information, sometimes they will not give the multiplicity, and then you have to get the multiplicity using the intensity field. So how much this intensity is there based on the intensity of some peak you will take as 100% and then you will calculate the intensity. Based on this intensity of the peak you are going to say that here two protons are there, here three protons are there. In another signal we are having only one proton or something like that we are going to estimate. We will discuss about this while when we are doing the structural determination. This is also estimated with using the nuclear overhauls and effect only. Okay, and here this NOE effect is very short range. Okay, only adjacent one, and there is a falling of 1 by R3, distance between the nucleus. R is the distance between the nucleus. So if you are calculate that if using the carbon hydrogen R value 1.49 angstroms, it will be there. Sorry, 1.45, very close to 1. Yeah, carbon normal carbon hydrogen is 1.1 or 1.2. It will be there. So with using that, if you calculate how much distance it is there, 1 by r cube distance. So if the atom is there in the nucleus is there between the 1 r cube distance, then that particular nucleus is going to have the effect on the adjacent nucleus. That way. So we can say that this NOE effect is very short range. So these are the scenes. You can see how it is working. So if you are having a two-spin system between the single carbon and then hydrogen atom, the effect of the coupling let out for the simplicity. So you can see how the effect will be there. You can see the how the effect will be, where it will have the more, where it will have the less. There will be four different combinations are possible. Okay, so that is 1 to 4, four different combinations are going to be possible in one. Two energy states where both are spin up or down are the lowest and then higher GML states. So that means N1, you can see this one. So when you are having carbon and then nucleus, carbon nucleus and then hydrogen nucleus spins are in the positive direction, you will have the lower energy. When you are having the carbon nucleus and then hydrogen nucleus in the downward state, you are having the higher energy. And between these two, so one is up and down, another one is here. Carbon nucleus is having positive and then hydrogen is having negative. Here carbon is having negative spin, hydrogen is having positive. Like this, the mixed is there, they will be there in between. Okay, they we can say that these two are degenerated states. So very small difference. The energy difference is very small. You can see the difference. So it's very small. And that's why roughly we can say that they are degenerated energy. That's why you will have the more intensity at that place at the lower and then higher. So and the origin of this MOE you can explain it using the quantum mechanics. These quantum mechanics are going to dictate that allowed transitions which are involved in allowed transitions which are involved. So they only one change at the spin and time. You see a single quantum transitions. These single quantum transitions are going to be allowed transitions. So allow transition. From here to here, only one spin change in the spin state, only one. Okay, from here to here also change its spin state only one, that is carbon. And here to here you will have only one spin state change. That is carbon spin state is changed from here to here. And from here to here, hydrogen has changed its spin state. But from here to here, carbon hydrogen spins are changed. This is not a allowed transition. This is a allowed transition. This is also allowed transition. This is also allowed transition. But this is forbidden transition. All are red color is confusing. So only one line I am going to turn. This is a forbidden transition due to the spin change in the two nucleus. And these are all allowed transitions. N1, N2, N1, N3, and then N4 transitions. N1, N2, N3, N4 transitions are allowed transition. So, if you talk about the equilibrium state, if you talk about the equilibrium state, the population of the equilibrium of two degenerated states, two degenerated states will be at N1 level, whatever the N1 level you are talking about this. So this is the highest one you will see, and it would be higher than the B value. Okay, a small amount delta. Okay, so what is the degenerated state at B is this one is the degenerated state. Is the degenerated state. Okay, N1 level would be higher than the B by a small amount of delta because of which. So two spin states we can parallel and N4 level it is going to be lower than the B. That is for this signal lower than this and with a small amount of delta. And here you are having two C13 transitions, that is N1 to N2 and then N3 to N2. N1 to N2 and then N3 to N2. Okay, these are the different transitions you can see here, and N4 level is going to be lower than the B, and N1 level is going to be higher than the B. And finally, this population, so this signal, and then this one, and then this one are going to give the information about us. N1 to N2 is the population signal, and N3 to N4 is also population signal. These two will give the information about the N1 and N4 level origin, N4 level populations, and at that place you are going to see the at that place you are going to see the signal intensity is going to be increased with that region. So still you can see there when a decoupler is used, when a decoupler is used, so what will happen? All these proton populations are distributed from their equilibrium values. That means, so from here to somewhere here it will be distributed, and the relaxation process restore these distributed populations to their equilibrium values. Here you are going to get the equilibrium transitions. So at this place we are going to get the equilibrium transitions. When you are decoupling the protons, you are decoupling the protons. These proton populations are going to be come back to the equilibrium transitions. So it will go to exit and then it will come back to the equilibrium. And then at this place they will be saturated. They will get the saturated stages. Okay. In that process, there will be a double quantum transition we can see. Where double quantum transition we can see, where both carbon and the hydrogen are going simultaneously they will relax. So there is a possibility of double quantum transition. At that time, the relaxation of the carbon and the hydrogen will have a simultaneously from N4 to N1 state. This leak in the upper state is going to enhance the population of the lower energy state of the carbon. This particular double quantum transition, whatever the particular double quantum transition is there, this we call it as a leak. Usually it should not appear, but it is also have a possibility of the appearance. And when a double quantum transition is going to occur, and so if this double quantum transition is occurring at lower state, the population of the carbon as well as hydrogen is going to increase. But when this carbon hydrogen population increasing at the lower state, here the intensity is more, you have a more energy. So this particular lower energy state is going to influence the intensity of the carbon, influence the intensity of the carbon. And that's why the when the population is larger and the signal is going to be intensified, and you will get a intensity. If the signal intensity is going to be increased, carbon signal intensity is going to be increased. In simple way, how you can say that when you decouple the product, if you confuse with the explanation, I will say it very simple. When you decouple these things, hydrogens will go here and then by relaxing and they will get a state that equilibrium state. But there is a possibility to before getting so some of you will be getting the equilibrium. This is one possibility. We are having one more possibility. And during the relaxation, it can come back to the lower state also. It can come back to the lower energy state. The hydrogens can come back to the lower energy state also. At that place, when it is come back to the lower energy state, so here the hydrogen population, the number of hydrogen nucleus will be higher here. And this population is going to, in the during the relaxation, this population is going to increase the intensity of the carbon. So this is the main process is going to occur here. A heteronuclear NOE effect is always observed in normal hydrogen decoupled spectra only. And this total NOE is for a given carbon, it is going to increase with the number of hydrogens. If it is more number of hydrogens, the signal intensity is going to be increased more. If it is less number of hydrogens, the signal intensity is going to increase less. Here you can see CH3 will have more intensity followed by CH2 followed by CH. Their carbon will have a less intensity compared to that because of the nuclear overhauser. And this is quite general. You can also apply in the homonuclear like proton-proton, proton yeah, carbon C13 also proton nuclear. But C13 is not very popular because C13 abundance is very less, so you will have a very less effect, and then the observance of the effect is going to be very less. It is not significant. So this is some of the examples you can see because of the hydrogens the intensity of the peaks are going to be increased. So you can see the carbon. Yeah. So this is 7, and then you can see the carbon. Yeah. So this is the first carbon. You are not having anything there. So if I write straight line, the intensity of the seventh carbon is more because of the three hydrogens present in this place. And then you can see second, 4, 5, 6 also. Yeah. Compared to 1, you are having more at the 2, and you are more at intensity more at the 4, intensity more at the 5 because due to the presence of one hydrogen in the aromatic ring, and then you are also having very less because here there is no hydrogen present in this place. Okay, and you are having electron. So these type of examples also you can see. So here very weak, no attached hydrogen, no NOE effect. Other signals are increasing more, but ipsocarbon is there. So this ipsocarbon is not going to be increasing its intensity more because options are